Yes, so I
You
can.
see the slide? So you see the slide and you hear me, right?
Yes.
Yes.
Okay. Okay, so let me start. So today we're going to talk about dimensionality reduction and one of the methods for dimensionality reduction, and this method is the random projection method. This is only one of many possibilities to do dimensionality reduction. Okay, so today I'm just going to present the setting, the goal, what is the problem, what we want, maybe see some small example, and I will describe the method, the random projection method, the guarantee, and we will see the proof in the next meeting. Okay, so what do we want? What is this topic? So we're going to talk about metric dimensionality reduction because there are many types of dimensionality reduction, but we will set ourselves to metric dimensionality reduction. So what is metric dimensionality reduction? So first of all, we are given a set of samples, X. It consists of n points, x1, x2, xn. So we are talking about finite sets of samples. Okay. And each point in this sample set, xi, is a vector of length d. So it's a d-dimensional vector. So for example, xi has d coordinates, right? xi1, xi2, xid. And we think of d as a large number. So we have n vectors, each of length d. And since we're talking about metric dimensionality reduction, it means that we have a distance function or metric defined over the points of x. It means that we measure the similarity between any two points in x by some metric, dxi xj. So there are many possibilities for metric, right? We have talked about it before. I think Eitan presented several metrics, possible metrics. Okay, and what's the goal of dimensionality reduction? So the goal, of course, is to find a map or function that maps the points in X into a k-dimensional space Y, such that Y has, as written here, k-dimensions, meaning that we want to map d-dimensional vectors into k-dimensional vectors. And we want this k to be as small as possible. We want to be small. But of course, we have to have some objective to optimize over, because we always can reduce into one dimension and lost all the information. So we want to preserve something. So in metric dimensionality reduction, we want to preserve the metric structure of X. Okay. So what does it mean to preserve a metric structure of X? So there might be many possibilities. Maybe sometimes we want to preserve the distances, sometimes we want to preserve the topology, or many possibilities. And also many possibilities for choosing the distance. So in this talk, I want to talk about the very basic scenario, where first of all, we set the distance function to be Euclidean distance, both in a high dimensional space and also in a low dimensional space. Okay, so what's this Euclidean distance? So what we are given this finite set of samples, right, X. And we are going to assume that the distance between xi and xj is just the Euclidean distance, the formula which is written here, which is basically just the length of the stride segment connecting xi to xj, right? This is how we measure it. And also we need the notion of distance on the space we are embedding into, right? Because we have the old representation and the new representation. And now we also have to define the distance in the new representation, in a k-dimensional representation. So we can set any distance depending on the application, right? But in this talk, I'm going to assume that we are measuring the new distances in the new space, in a k-dimensional space, also using the Euclidean distance. Yeah? So again, the new distance between any two images, yi and yj, is just the length of the stride segment connecting yi and yj. Okay, so what we have again, so we have an input set, n samples, each of length d. There are distances between any two points, which are Euclidean distances. And we want to find a map that maps points in X into a k-dimensional space such that now each xi becomes f of xi, becomes a k-dimensional vector, and we want the objective we are looking for is to preserve the distances for all pairs. Okay, this is the objective of metric dimensionality reduction. What does it mean? So we want the new distances for all pairs in X. There are many pairs in X, right? So we want for each pair in X, if we are looking at the new points in the k-dimensional representation, right? These are fxi and fxj. These are two short representations of high-dimensional vectors in low-dimensional space. So when we are computing all the new distances, or for each distance a new representation, we want it to be as close as possible to the original distance. And we want this for all pairs.
And
is it okay?
Yes, I understand. And I have a question. So if the set of points we started from represents the distribution of choosing the data, and I choose another point, can I get any guarantees on the reduction as well, or that's out of the scope of what we're doing here?
Yeah, so here so here you are not required for the new point that arrived. So you're talking about, okay, we have some endpoints and then now new point arrives.
Yes.
So what should I do? So I have a map, I can map it into a k-dimensional space. But here in the map that we will see that we are guaranteed to have, it's not necessarily true that this distance of the new point to the rest points will be preserved. It's not guaranteed here.
And if the new point is close to one of the original points?
So sometimes you can require this, and actually there are such maps that can preserve also the distances to the new arrived points with high probability. Not always. But there are also dimensionality reduction methods that guarantee this kind of property also. And actually one of them is built on this random projection method.
Got you.
Yes, it's a very, very nice property actually you're talking about. It's very important in practical settings to preserve also the new distances of the new points that arrive. Yeah. So what I also wanted to tell here is that so here it's a very particular case here we are talking about, right? Because what we want to preserve is something very, very specific. This is very important to understand what kind of metric structure we are preserving here, or we are requiring to preserve. We only require here to preserve just the distances, looking at all pairs of the original distances and all the pairs on the images. We just want to keep the new distances as close as possible to the old. This is all. We are not requiring here to preserve topology or the number of holes in the data, or I don't know, there are many, many things we can require to preserve depending on the problem we have, depending on the problem we want to solve. Because what's the use cases of dimensionality reduction? We have high dimensional data and we have some problem we want to solve on the data. So what we do in many cases, we just reduce the number of dimensions into smaller number. And now we're trying to solve our original problem on the reduced number of dimensions, right? So it depends what's the problem we are trying to solve. If the problem we are trying to solve heavily depends on the geometry, on topology of the original data set. So in this dimensionality reduction, we would like to require the preservation of topology, right? It's very important what is the problem we are trying to solve. But in many cases, the problem we are trying to solve, the only thing which is important is just the distances. And it doesn't matter what topology it is or whatever. Only the distances are important. So if I have in reduced space, if I have all the distances are very close to the, 1 minute. So if we have in the new space, all the distances being very, very close to the old distances, so I can solve my problem on the new distances, right? I will just lose only small amount of information. And the solution on the new distances will be roughly as the on the original distances, right? For example, if my problem is just clustering, I want to see what are the clusters according to, let's say, Euclidean distance I have in high dimensional data. So many algorithms of clustering depend on the dimensionality of the data. So I want just to reduce the dimensionality and just to keep the distances close to the original. That's all I want in clustering. I don't need to know if these data points, they are horse or they are cat or whatever. I just need to know what are the distances between the pairs. It's enough to solve the clustering problem. Okay, was it clear, this note, what I told just now?
Can I ask a quick question?
Yeah.
Hey, so is the dimension on the new space, you mentioned y is the number of dimensions, is that fixed, or is this algorithm going to give us what is the best number of dimensions that can be derived?
Yeah, it's a good question. I didn't tell here what is this K, but I just described the problem of dimensionality reduction, that we want to have two objectives here. One, K is very, very small, and second is the metric structure is preserved. And these objectives are competing between them. So we want to describe this trade-off. What's the number of them for a given number of dimension, how much of structure we can preserve, and vice versa. If you want to preserve some specific amount of structure, so how large the dimension should be. So this is the trade-off between these two, which ideally we would like to have a mathematical formula describing exactly what's the relation between these two. Yeah, so in our case of random projection, I will give exact formula which relates these two parameters. So you can pick K and you will know what's the number of, what's the amount of metric structure you preserve.
So some of the clustering algorithms will be dependent on the triangle inequality, right? So the triangle inequality will have inaccuracy that do you have any my question is maybe formulated this way. Do you have any dependencies on the accuracy where you kind of accumulate the error in some sense on the problems you can solve? Because it's not exactly the same, right?
It's not exactly the same, that's right. And the guarantee to preserve all the distances within some error, I think from this one you can deduce how much you will lose on triangle inequality.
So maybe I can't solve everything. I can solve things as long as accumulating error is not a factor, basically.
And also sometimes you want to preserve triangle. Sometimes you want to preserve for each 3 points, or for each triangle you want to preserve maybe all its lengths up to some factor. So this is a little bit different guarantee than preserving each pair separately. It's a little bit maybe relaxed guarantee. So this would be a different kind of maybe dimensionality reduction. Yeah, so this is very important to understand what you want to preserve. What is important to preserve for your problem at hand that you're trying to solve? Because sometimes it is important that you have reduced from horse in high dimension to a cat. After a dimensionality reduction, you got a picture of a cat. So if your problem is to classify cats and horses, so it's a horrible dimensionality reduction. You don't need it. But what if you just want, but maybe all the the pairwise distances between horse and cat, maybe they're very similar up to some factor. But for your problem, maybe it's enough. So it's very, very important to understand what problem you're trying to solve. And yes, and for
So they go together.
yes. And Ruth, Маша. Я просила, чтобы она выходила. Sorry. Okay, so let's see a small example. Okay, so our setting, we are talking just about Euclidean in the original space, Euclidean at the destination space, and we want to preserve each pair of distances. This is so-called worst case guarantee, because there are also guarantees that require sometimes to preserve most of the pairs and not all pairs, okay? Maybe sometimes you don't care about some pairs and you regard them as outliers. So sometimes it's enough to preserve maybe only most of pairs or something like this. So it will be a different type of dimensionality reduction and many other variants. Okay, so a small example. So let's think about a two-dimensional triangle with edge lengths being 1. All lengths of all edges is 1. So what are the vectors of the nodes of these triangles? So these are two-dimensional vectors. So I wrote here the coordinates. Node x1 has coordinates 0, 0, x2, 1, 0, and x3, this weird vector. So let's check that this represents length 1 in Euclidean space. Yeah? So let's compute the length of the edge x1, x3 in Euclidean space. So we have the formula, right? We have to take each coordinate in the first vector minus the coordinate in the second vector to the square, sum, square root, and we see that it becomes 1. Okay, so if you do this for all pairs, we have only 3 pairs of points here. So all of them have length 1. Okay, so we have a finite set of vectors x1, x2, x3 in two-dimensional space. All the distance is 1 in Euclidean space. And let's assume we want to reduce dimension into one-dimensional space. And we want, and the objective, as we told, what we are interested here is only to preserve the pairwise distances. Okay, so we want 3 new distances to be as close as possible to 1. Okay, so we can put x1, x2 at the distance 1. So we preserve the first distance, x1, x2. Now we can put x2, x3 at distance 1. So we preserve the second pair of distances. And now we have the third pair of distances, right? x1, x3. So it was at distance 1, and now it becomes at distance 2. So we couldn't preserve exactly, right? And it doesn't matter how much hard we try here. In one-dimensional space, we cannot do better than this, right? If we want to preserve all the distances. It always will be distorted. At least one of the pairs will be distorted. So this pair x1, x3, it has been distorted. So it's expanded, right? It was of length 1, and the new length is 2. So it expanded by factor of 2. So we succeeded to preserve 2 distances, 1, 1 exactly. And the third one, we preserved up to a factor 2. So basically, this dimensionality reduction method is quite good because it only has error of factor 2 on one of its pairs, which is kind of a small and practical situation. Yeah, it didn't expand by 100 or something. It's just factor of 2 error. So we consider this as a good metric dimensionality reduction. But someone else can tell me, no, it's not so good because I had a triangle, I had some geometry here, I had some topology here. And now in a small number of dimensions, I have nothing. I have 3 points that have nothing to do with triangles. It didn't preserve any property of triangles, maybe. Yeah, so it depends what you want to preserve. If you want just to preserve the pairwise distances, this is a very good dimensionality reduction. Okay, so again, we have endpoints. We are going to reduce dimension for a finite data set of points, not infinite, not for the whole d-dimensional space. No, we have a fixed set of endpoints in d dimensions, and we want to embed them into k dimensions. K is small, as small as possible. And we want this guarantee that the new distances and the old distances are preserved up to factor alpha. And we want this alpha to be as small as possible. And actually, we want the exact trade-off between alpha and k. Okay, so how can we achieve this? So there are actually several methods for dimensionality reduction that can describe this trade-off. I'm going to talk about one of the most classic and very, very nice methods. I really like it. So it's called the random projection method. And it was proved by mathematicians in 84. And it's also called the Johnson-Lindenstrauss transform. And one of the authors, one is a mathematician called Johnson, and the second one is Lindenstrauss. And the Lindenstrauss is Israeli mathematician who was in Hebrew University. And so what they proved basically is that if you have these endpoints at your hand with Euclidean spaces, so what you can do is you just can randomly at uniformly pick a k-dimensional subspace. Just pick one, so you have some k. So just pick one of these subspaces, random, uniform at random, and project your points into this subspace. So if you set k to be large enough, so you're guaranteed with high probability, because this is a randomized algorithm, it's a random algorithm, because you're picking a subspace randomly. So with high probability, you're guaranteed that all the pairwise distances will be preserved if k is large enough. And this is a very nice result. It's not so obvious. So they showed actually how large k should be. So they showed that if you choose k to be, as what is written in theorem here, some constant, let's say 10, basically it should be roughly log of number of points over epsilon square. So if you pick k-dimensional subspace of this number of dimensions, uniformly of random over all k-dimensional subspaces, and you project your points at either one of these, so with high probability, all the pairwise distances will be preserved within 1 plus epsilon factor. Okay, it means that the new distances and the old distances will be differ by this small error, multiplicative error, 1 plus epsilon error, which is very, very small. And what does it mean with high probability? It means that for most of these subspaces, if you project into this subspace, so the distances will be preserved. But for some, it will not. But for a very small fraction of this. So don't worry, if you really are going to pick one, so with good probability, you will pick the good one. This is a very nice result, but the thing is that it's not algorithmic, right? Because we want an efficient way to embed our points. Now, how can I write a Python program that picks uniformly at random k-dimensional subspace? It's not so easy. It's not actually an algorithmic result. It's a mathematical result. So then
what happens if we're talking about the Euclidean space and you just choose a random k dimensions and set all the n minus k dimensions, d minus k dimensions?
So exactly this is the result of from other researchers that show that you can implement it like this, which is not picking uniformly at random subspace, but it picks a good enough random subspace.
Yeah.
You have to prove it, and this is the first algorithmic result. And I'm going to talk about a little bit different algorithmic result. But you're right. This is one of the methods you can approximately choose a uniform at random subspace of dimension k.
And is it dependent on the choice of the base or not?
No, if you have it the base uniformly at random, so no, it shouldn't be dependent. Because the base, you have to choose the orthonormal base.
Right.
So it will not be dependent. And this is why you are scaling a little. So I'm going to talk a bit some similar approach, a little bit different. So one of the ways to do it is as Aidan told, and the second one I'm actually going to talk about here because this one is implemented actually in Python. So what in 94 other researchers, Indik and Batvani, they showed that actually you don't have to pick exactly uniformly at random. You can pick roughly uniformly at random, and you don't have to pick exactly subspace. You can pick roughly subspace, meaning the basis you are choosing shouldn't be exactly independent. Shouldn't be exactly independent vectors. But with high probability, whatever you pick would be close enough to being uniformly at random subspace. So how to do it? They say, okay, so we are setting epsilon. This is an error parameter. This will be an error on the distances. And we pick a matrix of size k is over times d. K is the number of new dimensions, and d is the number of original dimensions. And each entry of this matrix, we pick IID independently from the other entries from the normal distribution. Okay, so each coordinate we pick from normal distribution some value independently for each one of these entries. And the embedding now, so this P is kind of a projection matrix. So the embedding now, to embed one point xi, we just multiply xi with this matrix, and we get k-dimensional vector, and we normalize it by square root of k. This is to guarantee that this matrix actually is kind of orthonormal basis with high probability. Okay, so what is the guarantee? So the proof, and I hope next meeting we are also going to prove this, that if we set k, number of new dimensions, to be logarithmic on the number of points set, divided over epsilon square, so with high probability, the new distances, all the new distances, will be up to factor 1 plus epsilon to the original distances. Okay? It means that for each pair, we have only very small error on the distances, only 1 plus epsilon. And this is this is the same guarantee as the original mathematical claim says, but implemented algorithmically. And what is interesting here is that you can notice that the new number of dimensions, it does not depend on the original number of dimensions. Okay? It doesn't matter how many dimensions we had. What is important is how many points we had. This is what will set the number of new dimensions we need in order to have a very small error on all pairs. Okay, and this number is quite small because if we had n points originally, so it means that in Euclidean space, n points can be at most of n dimensions. Right? You can always represent n points in n dimensions. Basically, it can be a nice exercise. So if you had n points, each point of dimension n, so in the new representation, you will have only logarithmic number of dimensions. It's a huge improvement in the number of dimensions. Yes, it's exponential improvement in the number of dimensions. And the error on the distances you have is very, very small. All the distances are almost the same, 1 plus epsilon. It's a very small error. And As I told, this is the probabilistic result, because the algorithm is randomized, right? Because you're picking matrices randomly. So there is a distributions of matrices, and you're picking one of these. But the result says that with high probability, you're guaranteed to have the distances preserved. What does it mean? It means that for most of the matrices in the distribution, if you pick one of these, you will have the guarantee. And only for a tiny fraction of the matrices, if you pick somehow one of these bad matrices, you will not have this guarantee. The distances will be distorted by a large factor. But this fraction is very small, so repeating your algorithm several times, you are guaranteed that in one of these repetitions, you will pick the good matrix for you. So yeah, so this is the result of random projection. And this is why it's called a random projection, because it stems from the mathematical result. And actually, if in early 2000 year, roughly in 2005, another researcher, he actually proved that if instead of picking entries of this matrix from normal distribution, you pick them from plus, minus, 1, and zeros distribution, okay? Each with the probability 1/3, third, okay? Because to pick from normal distribution algorithmically, it also takes time, okay? To simulate in computer picking number from normal distribution, it takes time. But if you just can substitute this normal distribution with distribution over +1, -1, and 0, so it's very efficient algorithm to pick one of such matrices, first of all. And the second, to compute multiplication of this matrix with xi will be much more efficient, because many entries will be 0. Roughly a third of the entries will be 0. So it's very fast to compute also such matrix. So he showed, a researcher in 2005 showed that you can pick also coordinates 1 plus -1 0 with uniform probability, and you still have the same guarantee, exactly the same number of dimensions and exactly the same error, which makes it also a very nice result. And I think they also have this implementation in Python, is 1 plus -1 0.
Why 3?
Why 3 numbers?
Yeah, why 3 options? Yes, 1, 0, -1.
So his motivation was to have sparse matrix for projection, to have as many zeros as possible. So to have fast multiplication, fast compute time to embed one. So he wanted zeros, and he couldn't afford only ones, because if you have only ones, you will accumulate in the computation of p times xi.
Yeah,
You will not be able to preserve even the norm of a vector. So you need minuses to reduce it.
so that's the minimum.
This is the minimum, right?
Yeah.
Right, you're right. This is the minimum number of options, if your goal is to have fast computation. So there is another line of research.
I could do also 1, 2, 3, 4, -1, -2, -3, -4, 0, and I will get something that is less sparse, right?
You will not have sparse because you don't have zeros. Sparse
No,
is
no, I have 0. I say I go 1, 2, 3, 4, -1, -2, -3, -4, and 0.
yes. So you will have only 1/8 entries, an expectation of zeros, fraction of zeros. Yes. Yes, and there is also a line of research starting from this work, actually trying to understand how sparse these matrices can be. And there are very, very different constructions that are very, very sparse, actually. And these state-of-the-art results, actually, now in this field of metric dimensionality reduction. We will not cover it here. Yeah, and also another line of research is trying to understand not only having sparse matrices, but sometimes a matrix is not sparse, but it's somehow structured. It has some special structure. And this special structure sometimes helps to compute in a fast way this multiplication time between P and Xi. For example, a matrix, Hadamard matrix, which basically encodes fast Fourier transform. So we know that, and it's very structured matrix. So we know computing fast Fourier transform of a vector, it's like computing Hadamard matrix by the vector, and it takes very fast to compute it. So there's also this line of research trying to see, okay, what other types of matrices, structured matrices, can guarantee these preservation properties and compute it much faster even than sparse matrices. Also line of research. But in the next talk, we will just consider this classic result with normal entries and maybe see at least some steps of proving this theorem, which uses several inequalities 8 and presented, union-bound Markov inequality, and maybe Chebyshev inequality. All three of them appear here in the proof. So I think it's nice to see application of these inequalities in this theorem.
Great.
Yeah. Okay, so that's all for today. Thank you.
Thank you. Any additional questions or comments?
Could you say a few words on how you will apply this? How is this going to be used?
Yeah. For example, as I told before, for example, in a clustering problem, okay, I have a data n samples, and this data in high dimensions. I don't know, like a 10,000 dimensions. And I have algorithms that can find clusters, but the running time of these algorithms depends on the dimension. So it would be, I don't know, like 2 to the power of the number of dimensions, the running time, roughly. Many of them are exponential in the number of dimensions. So it's infeasible for me to compute these clusters in this high number of dimensions. So what I can do, I can apply this method and into log of 10,000 number of dimensions, and now compute my clustering on the new number of dimensions in a very small number of dimensions, actually. And it will be much, much faster. Now it becomes feasible. So I compute new clusters, and I know the images, and I know the sources of these points. So the cluster on the images, I can now interpret it into the clusters in the original space, right? So I can just now deduce what is the clustering on the original samples from the clustering on the embedded points, which I computed very fast because the dimension was small. For example, one of the direct uses of these dimensionality reduction methods. And also there are many applications also in online algorithms, but these are mostly theoretical application, I think. Yeah, I don't want to get into this actually. This is one of the straightforward applications I know in practice, in real life problems.
Yeah, no, makes sense. Thank you.
Yeah, thank you.
So if I conduct a gradient descent in the reduced space, are there any kind of techniques that will guarantee that the gradient descent in the original space is still meaningful, the matching?
It's a very, very, very good question. I don't know, but I think this question was investigated by researchers. It sounds very natural and applicative question. I don't know, and I don't see while this random projection method would preserve. But maybe I'm wrong. Maybe some deep mathematical result is hiding here. Yeah, I don't know the answer to your question. That's a very good question.
Maybe let's think about it. Let's talk about it also offline. Maybe.
Yeah, that's a very good question, I think. And I guess it wasn't. I'm actually. I will try to search in the literature if there are some results on this.
Thank you.
Thank you. Thank you.
Okay, thank you very much, and we'll continue next time.
Yeah. Bye.
Bye-bye.
Bye, thanks.